Hi everyone, so today we're going to talk about more big and huge stars and their stellar evolution here. So these stars are going to start out pretty much the same as all, but they're probably going to start with our more massive stars here. So when we're looking at an HR diagram, we're going to look at where the mass is higher in the main sequence. After their main sequence, they move into a bright supergiant. Then they are either a big star or a huge star at that point, and after our supernova explosion, they'll either turn into a neutron star or a black hole, depending if they're descending from a big star or a huge star. So if we take a look at the structure of an old age of our big and huge stars, you're going to see much more layers here. So again, we have an hydrogen fusing cell, helium, then we move up to carbon, neon, oxygen, silicon, to finally iron. So as you can see, there's a ton more shells here, so we're burning a lot hotter, a lot faster. But now that the old star's core is made of iron, iron cannot be burned. So since iron cannot be burned, it can't to make any heavier elements. So the star core is going to collapse because of the gravity, and then it's going to explode, and that explosion is going to be a supernova. So that's where that's going to occur. How fast does this happen? So if we look over all those different shells, we can see that in 7 million years, that's when we move into our hydrogen fusing stage. After 500,000 years, we're going to see our helium fusion. 600 years, we have our carbon fusion. 1 year, we'll see neon fusion. 6 months, we'll see oxygen fusion. 1 day, we'll see silicon fusion. And then our core collapse will happen in 0.2 seconds. So it's such a small number here that, as you can see, as we progressively go down to the different substances that we're burning, that it gets shorter and shorter, each element that we start burning here. And then we'll have our core bounce, and our supernova explosion will last for hours here. So that's just how quickly this really occurs. So once we get to silicon, it's not much time left until we'll see that supernova explosion. So our supernova here is going to make a huge mess. As you can see, this simulation, once 10 milliseconds apart, we'll see much more different mess. It's very chaotic, and this computer simulation is just showing the chaos that we see deep inside the star when it starts that explosion. So again, this is only 10 to 20 milliseconds from the beginning of that explosion after the core has collapsed. So our remnants here, we're going to see different clouds that we'll see. So this is an example of our Cygnus loop. And again, that supernova explosion is going to cause those different clouds to be made. A gum nebula, so this was created by a supernova 11,000 years ago. And it's known to be the largest supernova remnants. And now it's about 200,300 light years in its diameter from end to end. So that's a really huge supernova remnants that we can see here. So just some more. We can see before, after. So we'll see our supernova. And then we see all these remnants here from after our explosion. So looking at our final stages, so neutron stars result from the supernova explosion of big stars, and black holes are going to result from the supernova explosions of huge stars. So a neutron star is going to be have about 1.5 solar masses and only about 20 kilometers in diameter, so it is still very large, but we're going to see a solid crust here with a fluid core. So this fluid core is going to contain many neutrons with other particles as well. So if we're taking a look, our neutron star has a superconducting superfluid core. So as we can see, we have superfluid neurons and superconducting protons here. We're going to see this superfluid, superconducting superfluid is going to be a very thick part of this star. Then after this, we have another mantle of superfluid neurons, which is a little bit less thick, and then our crust is going to be only about 0.3 kilometers thick. So we're going to have mostly of this superconducting superfluid, which will contain most of the star's interior here. So how big really are these neutron stars? How dense? So a neutron star would typically fit between Loyola Academy and Chicago's Loop, so we can see that's going to be most of our United States, starting from top to bottom. So that's a really large location, so 20 kilometers if we can look at that. And then how dense would it be is a teaspoon of neutron star material would weigh 1 billion tons on Earth. So it's a very, very dense star that we can see here. So this is where we're going to stop for now. We're going to talk about the ending of huge stars next time. If you have any questions, make sure you ask.